Hello everyone. Welcome to part 2 in our series on solving differential equations using Laplace transforms. Today we're going to be looking at the Laplace transforms of several basic functions. Okay, so here's the definition of the Laplace transform that we learned last video. We use an input function, little f, and out comes an output function, big F. Now, you can see that the structure of the integral is a function times e to the minus st. Commonly, to do those integrals, we use integration by parts. So I'm going to assume that you're familiar with integration by parts. I'm going to review that right now, but it's going to be kind of a quick review. And I'm also going to use tabular integration, which, if you haven't seen before, is basically integration by parts, just without all the symbols. Okay, so for example, let's say we want to do the integral of x e to the minus ax. Okay, I take my function, which I regard as u, and I put it in a column over here. I take derivatives of that function. So the derivative of x is 1. The derivative of 1 is 0. I stop when I get to a 0. I make a second column, which is just alternating plus, minus, and plus. And I make a third column using the v function, really dv, right? I put that up here, and I take integrals of that function as I go down the column. So the next column member is minus 1 over a e to the minus ax. I integrate that again, and I get 1 over a squared e to the minus ax. I draw a couple of diagonal lines, and I've made my table. This is basically why it's called tabular integration. I've got a 3 by 3 table. Okay, what do I do with all of this stuff? Well, I multiply the functions at the ends of the diagonal lines using the sign right above the diagonal line. So my first term is minus x over a e to the minus ax. My second term comes from this diagonal line. Multiply with a minus sign. So that's going to be minus 1 over a squared e to the minus ax. And if you do this by traditional integration by parts, you should get the same thing I did. I just didn't use any of the symbols, u and dv and v and so forth. Okay, that was our super quick review of integration by parts. Let's actually do a Laplace transform. Okay, the first function I want to take a Laplace transform of is e to the at. Okay, here we go. F of s equals 0 to infinity, e to the minus at, e to the minus st dt. Let's combine that all into one exponential. So that's e to the minus s minus a t dt. Okay, I wrote it that way because you can see that s has to be bigger than a in order for this exponential to be negative. If this is a positive exponent here, then this integral is not going to exist because the exponential function is going to blow up as t goes to infinity. So we're going to need s is greater than a. But given that, we can actually do this integral. Remember that s and a are essentially both constants. So I get minus 1 over s minus a e to the minus s minus a t, and we have to evaluate that at infinity and at 0 and subtract. Okay, as t approaches infinity, which is the meaning of putting infinity right here, as t gets very, very big, what happens here, if s is bigger than a, this goes to 0. So I just get 0. Minus, what happens as t is 0? Well, this just becomes 1, and I just get minus 1 over s minus a. So my final answer is 1 over s minus a, as long as s is bigger than a. That is the Laplace transform of e to the at. And that's a nice little formula. We can use a as a variable. If a is 2, then the Laplace transform of e to the 2t is 1 over s minus 2, as long as s is bigger than 2. Okay, let's do another. F of t equals t. Okay, our Laplace transform is t e to the minus st dt from 0 to infinity. Can you imagine if this integral were on a test? It's a test integral. Ooh, that's a bad joke. Okay. Here's our result from last time. We can actually use this really straightforward, really perfect for this integral. We just have to apply the bounds. And obviously the variables are a little different, but we already did all the work here. So I'm just going to use this result in green using the right letters. So I get minus t over s e to the minus st minus 1 over s squared e to the minus st. And we have to evaluate that at infinity and 0 as usual. Okay, this is a little tricky. T is going to infinity. This is getting really big. T is going to infinity here as well. This is becoming close to 0. Which one wins? Turns out that the exponential goes to 0 more quickly than t goes to infinity. So the limit as t goes to infinity of this term is actually 0. And you've probably seen that before using L'Hopital's rule. Okay, next term. If t is infinite, then the exponential, again, is 0. I just get another 0. Okay, minus. Okay, now we're letting t become 0. What happens to this term? Well, I get another 0. I hope we don't get all zeros. Finally, oh, here we go. This term, e to the minus st, becomes 1. So I get just minus 1 over s squared. So I get my answer, 1 over s squared. S has got to be bigger than 0. Otherwise, this function just becomes infinite as t goes to infinity. So the Laplace transform of the function t is 1 over s squared. We're adding to our library that we're going to use when we solve differential equations. Okay, let's do one final transform, very important, of a trigonometric function. Okay. F of s equals the integral from 0 to infinity of cosine at e to the minus st dt. And once again, this is a perfect integral to do using tabular integration. Okay, let's do it up here. I'll put it in a different color so that we don't get confused. Cosine at plus, okay, so I take derivatives of this function, minus a sine of at, minus a squared cosine of at, plus, minus, plus. I'm going to take integrals of this function, so that's e to the minus st, minus 1 over s, e to the minus st, 1 over s squared, e to the minus st. Great. I'm going to draw my diagonal lines, as usual. Okay, we're ready to go. F of s equals, okay, multiply these functions with a plus sign. So that's minus cosine at over s e to the minus st. Multiply these functions. I got two minus signs, so those are going to cancel and give me a over s squared sine at e to the minus st. Now here's a really great thing with tabular integration. If I want to go across a row as opposed to diagonal, then I just introduce an integral sign. Cosine at e to the minus st dt. There we go. That is our function f of s. I know this looks terrible, but something's happening here which is really useful. Look at this integral right here. This integral is f of s. Don't forget that we're going to evaluate this part from infinity to 0. Okay, so what does that mean? We get f of s equals, okay, this term, as t goes to infinity, this term goes to 0. This term, as t goes to infinity, also goes to 0, so we don't have to worry about that part. As t equals 0, well, this term with a sign in it, that's going to become 0. All I'm going to be left with is this term. This guy is 1, and I get minus 1 over s. But remember, I'm subtracting the lower bound, so I actually get 1 over s. That was everything that comes out of this part. Okay, and I still have minus a squared over s squared times f of s. That actually simplified really nicely. Okay, I have to solve this equation for f of s. So I'm going to bring f of s over to this side, and I get 1 plus a squared over s squared f of s equals 1 over s. I might run out of room here, so let's move that a little bit. There we go. Okay, solve this finally for f of s, and I get s over s squared plus a squared. Okay, I went through quite a few steps there. That was a really challenging one. So go through it slowly yourself to make sure that you get what I got. That's the Laplace transform of the cosine function. Okay, let's summarize all that work we just did. Here's our table. Laplace transform of a constant, we did that in video 1. These 3 integrals we did today. And I didn't do the sine integral. That's a good exercise for you to try yourself. It's very similar to the cosine integral. We're going to use all these results in our next video when we do solving differential equations. Okay, that's it for this video. I hope you enjoyed it, and I'll see you next time.